Welcome to this lecture in the ongoing series of lectures on real analysis. Today we'll be starting a new module and it will be about power series. Slowly we are progressing and developing material that we need to define what is called the exponential function and the logarithmic function and the trigonometric functions. This is one very crucial module for it. So before we get into power series and the relevant theorems, we need to recall some basic facts that we have proven earlier. So one of them is the root test. What does it say? It says that suppose you have a series and then you associate to it some funny looking number, alpha, it could be infinite. Then the series converges if alpha is less than 1 and the series diverges if alpha is greater than 1. If alpha equals 1, then we can't say anything either way. But in these two situations, we can comment on the convergence of the series. And recall that we also did this exercise that this lim sup, in fact, this limit exists and is equal to 1. So just recall that. Basically, you need to be able to figure out such things to at least have a very good handle on most of the series as to their convergence. Okay, so this is something that we did earlier, and another thing that we'll need is the M-test, Weierstrass M-test, which is about the uniform convergence of, it's a criterion to decide if a given series of functions is uniformly convergent. So given a sequence of functions, we can form this series of functions, and then the Weierstrass M-test says that suppose you have a sequence of numbers m1, m2, m3 such that fn is bounded by mn pointwise. For each little x, this absolute value is bounded by mn. Then this series converges provided this series converges. So it's a very useful test, and we'll see how is it useful. Okay, so let us define what is a power series. So what we have is we have a sequence of real numbers. And to this sequence of real numbers, we can associate what is called the power series of the sequence, which is just a formal expression given by this symbol. Right now, this is just a symbol. You just decorate this extra x to the n. And we'll see how we associate real numbers to it, but so far it's just this much. And these an's are called the coefficients of the series. So an is the nth coefficient, and note that this is starting with 0. Okay, so very simple definition. So far nothing has happened. And now what we will associate to a power series is its radius of convergence. So given a power series, what we can do is we can think of x as a real number and then ask if this series converges. Right? Once x is a real number, this is a real number, and hence this is a series. And then we can ask the question if this converges. So given a power series, can we characterize for which real numbers x the series converges and for which real numbers x the series diverges? So it turns out that this has a very nice answer. And it is as follows. So you fix a power series and then write alpha as this again, that funny looking thing that you see in the root test. Then this power series, meaning this power series, converges absolutely for each real number x satisfying this inequality, where what is r? R is 1 upon alpha. And I should mention that if alpha is 0, which it could be, then r is to be taken to be infinite. And if alpha is infinite, then r is to be taken to be 0. So the convention is 1 upon 0 is positive infinite and 1 upon infinite is 0. So under this convention, we have written this equation. Okay, so once you have this alpha, you define r in this fashion, then the theorem says that this series converges absolutely for those x's which satisfy this inequality and diverges for those x's which satisfy this inequality. And if you have mod x equals r, then we can't say anything. then we have to specifically get into these this particular series that we have and investigate and decide what happens there. But this is a pretty good answer to the question of convergence of the power series. In fact, it is giving you either absolute convergence or divergence. The only point of contention that remains is mod x equals r, which we won't bother with much. Anyway, so how do we prove it? Well, we'll just hit it with the root test and it'll pop out. The proof is very, very simple. So let Bn be this. So fix a real number x. Let x be some real number. And define Bn as an x to the n for n greater than equal to 0. So for each n we have that guy. Then the lim sup of this, as you can easily see, is this thing. Which is by definition of R equals to that. So by the root test, this series converges if this is less than 1 and diverges if this is greater than 1. And that's it. That's basically what the statement here is. So that is the proof. Right, very simple. Oops. Yeah, so this allows us to define what is called the radius of convergence. This is called the radius of convergence, this R. It's called the radius of convergence of the power series. Okay, so to each power series we have a number called the radius of convergence, and if you pick a real number, so we have this real line, this is 0 and r is the radius of convergence, this is plus r, this is minus r. And if you have a real number within the radius of convergence, meaning within this interval, then for that real number the corresponding series converges absolutely, and if you take a real number outside that, then the series will diverge. So that's what we have proven. Okay. So now we can actually say something more. We can show uniform convergence of this series under a certain little bit of a compromise on the radius of convergence. So here is the precise statement. So you fix a power series and R be its radius of convergence. Then for each epsilon greater than 0, the power series not just converges, it converges uniformly on a little bit edited region. So this was minus r, this was plus r. So now what we have is we have just chopped off a little bit of this whole interval and gotten this minus r plus epsilon and r minus epsilon. So in this region the power series converges uniformly. So let's prove it, and we'll prove it using the M test. And again, the proof is not going to be complicated. So let x be a real number such that or maybe I shouldn't write it this way. So for all x in this interval, we have, and I'm writing something very, very trivial. We have an x to the n, absolute value is at most an r minus e to the r minus epsilon to the n. So I haven't done any great thing. Okay, so now this series of functions okay, maybe I should write, yeah, so this series of functions where x is taking values from this interval, this series of functions is what we are concerned with, and we'll show that this series of functions is uniformly convergent. So interested in this series of functions where I should mention that x is taking values from this region. Now, here is the thing. The nth function of this series is bounded by this guy, and let me call this mn. So this number will be called mn. Right? This is the nth function in this series. So I hope you understand x. When I write x, well, it's a real number, but you can think of this expression as a function which takes little x to this guy, to this guy. So the nth function has this bound, and this is for each x. This is for all x, right? For all x in this domain. So this is our mn, and now this summation is finite because this power series, the original power series that we have, is absolutely convergent at x equals r minus epsilon. So if you substitute x equals r minus epsilon, then the fact that this guy converges absolutely at r minus epsilon says that this is the case, meaning this summation is finite. Why does this guy converge absolutely at x equals r minus epsilon? Because if x equals r minus epsilon, then x is within this interval minus r comma r, and for any x within this interval, you have absolute convergence of the power series. This is precisely what the previous lemma was. So therefore, this is finite, and now by the m test, we see that converges uniformly. In this domain. And this is what we wanted to prove. So let's go over this once more. we are interested in this series of functions where x is taking values in this interval, and if we want to apply the m-test. So how do we apply the m-test? We estimate the nth guy, and for each x this estimate holds. That's a trivial fact. And let us just call this guy mn, and because every power series converges absolutely for any entry within the radius of convergence, we have that this guy is finite, and this is all we need to apply the m-test, and therefore we see that this series converges uniformly in this domain, and that's what we wanted. So why are we caring so much about uniform convergence? Because we care about that because uniform convergence allows us to show the limit of a bunch of functions or a series of functions or whatever. We can deduce the niceness of the limit using the niceness of the summands. So this is why we care about uniform convergence. It is important to establish this so that when we can differentiate power series, etc., and say something about the derivative of the limit function. So we'll get there. And I guess this is all for today. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.